We thought capturing a black hole was the breakthrough. It wasn't. What's more unsettling is that the object at the heart of this galaxy doesn't need to swallow stars to control a realm spanning hundreds of thousands of light years. The galaxy M87 appears calm, with little star formation and little visible chaos. Yet its core hides a machine of energy that never truly rests. A black hole doesn't just bend light. It reshapes the fate of everything around it. And today, we will not ask how big it is, but how it has come to rule an entire galaxy. To understand what we truly saw in the first image of a black hole, we need to step back, far beyond the image itself, and place it within its proper cosmic setting. That setting is a galaxy known as M87. M87 is not an ordinary galaxy. It is a giant elliptical galaxy, one of the largest in the nearby universe. M87 resides at the heart of the Virgo cluster, a massive collection of thousands of galaxies bound together by gravity. This cluster itself is a dominant structure in our region of the cosmos, and M87 sits near its gravitational core. The galaxy was first identified in the year 1781. It was catalogued by the French astronomer Charles Messier. Messier was not searching for galaxies. He was hunting for comets. In that process, he catalogued fuzzy objects that could be mistaken for moving objects in the night sky. M87 was one of them. At the time, no one knew what M87 truly was. The concept of galaxies beyond the Milky Way did not yet exist. What appeared as a faint smudge through an 18th century telescope was, in reality, a system containing trillions of stars. Today, we know that M87 lies about 55 million light-years away from Earth. That distance is large, but in cosmic terms, it is relatively nearby. Close enough for us to study its structure in detail. Close enough to observe its core with unprecedented resolution. Visually, M87 appears smooth and featureless. Unlike spiral galaxies, it has no sweeping arms filled with bright blue stars. Star formation in M87 is minimal. Most of its stars are old, long past their most active phases. By many measures, M87 should be a quiet galaxy. But its center tells a very different story. At the heart of M87 lies one of the most extreme objects known in astrophysics, a supermassive black hole known as M87 star. This black hole contains a mass billions of times greater than that of our Sun. It is not merely heavy, it is gravitationally dominant on galactic scales. In 2019, this object became the first black hole ever directly imaged by humanity. The image was produced by the Event Horizon Telescope, a planet-sized array of radio observatories working together as one. What we saw was not the black hole itself, but its shadow, cast against glowing material swirling at the edge of no return. That image quickly became iconic, but it also created a subtle misunderstanding. It made the black hole feel like a static object, something isolated at the center of a galaxy. In reality, M87 star is anything but passive. Its presence defines the behavior of the galaxy around it. It shapes how gas moves. It regulates how energy flows. And it influences whether new stars can form at all. To understand M87, we cannot look only at its stars. We have to look at its core. Because in this galaxy, the center is not just another region. It is the engine. If M87 star is just a black hole, why does it appear capable of dominating an entire galaxy? When we say that a black hole dominates its galaxy, the word itself can be misleading. It invites an image of relentless gravity pulling everything inward. Stars spiraling toward destruction, entire systems collapsing into darkness. But that is not how domination works in M87. In fact, the black hole at its center barely touches the stars at all. The vast majority of stars orbit peacefully, far beyond its immediate gravitational reach. On stellar scales, the black hole is almost irrelevant. Yet, on galactic scales, it is decisive. The key is that M87's black hole does not rule through direct force. It rules through energy, not by consuming everything around it, but by controlling how matter behaves long before it ever comes close. To see this, we need to shift our focus away from stars and toward gas. Galaxies are not just collections of stars. They are also vast reservoirs of hot gas, cold gas, dust, and plasma. This diffuse material is what fuels star formation. It is also what responds most dramatically to energy. At the center of M87, gas does not simply drift inward. As it approaches the black hole, it is heated, compressed, and accelerated. Temperatures rise to millions and even billions of degrees. Under these conditions, matter becomes an efficient carrier of energy. The black hole does not need to pull on distant regions directly. It only needs to inject energy into its immediate surroundings. From there, that energy propagates outward through the galaxy. In M87, this process is extraordinarily efficient. The central black hole releases vast amounts of energy into the surrounding gas. This energy prevents gas from cooling, and gas that cannot cool cannot collapse. Without collapse, new stars cannot form. In this way, the black hole regulates the life cycle of the galaxy. It does not destroy the galaxy outright. Instead, it quietly determines what the galaxy is allowed to become. This is sometimes called feedback, but the word feedback can sound abstract. In reality, it is deeply physical. Energy released near the black hole pushes against surrounding material. It stirs the gas. It inflates regions of low density, and it redistributes matter across vast distances, over millions of years. This reshaping becomes visible on galactic scales. Importantly, this dominance does not require constant feeding. Even relatively small amounts of infalling matter can produce enormous energetic output. The black hole acts less like a vacuum cleaner and more like a regulator. It controls the conditions under which matter exists. It sets limits on temperature and density, and by doing so, it controls the future of the galaxy without ever touching most of it. This is why size alone is not the answer. The true power of M87's black hole lies in influence, not consumption. It dominates by shaping environments rather than erasing them. And that kind of control leaves traces, not in the orbits of stars, but in the structure of gas itself, which leads to the next question. If this invisible power is real, what physical marks does it leave behind inside the galaxy of M87? If the black hole at the center of M87 truly dominates its galaxy through energy rather than gravity alone, then that influence should be visible, not as a dramatic explosion, not as a sudden act of destruction, but as long-lasting imprints written into the structure of the galaxy itself. Astronomers began to notice those imprints when they stopped looking at stars and started looking at hot gas. In galaxies like M87, Most of the visible mass is not locked into stars. It exists as vast clouds of gas filling the space between them. This gas is heated to tens of millions of degrees. At such temperatures, it shines brightly in X-rays. When astronomers observed M87 in X-ray light using the Chandra X-ray Observatory, something unexpected appeared. The hot gas was not smoothly distributed. Instead, enormous cavities were carved into it. These cavities were vast, each one spanning thousands of light years across. They contained little to no hot gas, and strikingly, they contained no stars at all. These were not empty voids left behind by chance. They had sharp boundaries and coherent shapes, almost like bubbles blown into the galaxy. The first question was an obvious one. What could possibly carve structures like this? Supernova explosions were an early candidate. After all, they release enormous amounts of energy. But supernovae act locally. They scatter energy in chaotic patterns. They cannot produce cavities of this size. Symmetry and persistence. Galaxy collisions were also considered. Mergers can distort gas on large scales, but M87 shows no evidence of a recent violent collision. Its stellar population remains remarkably smooth and undisturbed. The cavities had to be carved by something else. The answer became clearer when astronomers compared X-ray images with radio observations. The cavities lined up with regions where powerful radio emission was detected. This was a crucial clue. Radio emission traces energetic particles moving at near light speed. In M87, those particles originate from the central black hole. As energy flows outward from the core, it pushes against the surrounding gas. Over time, this pressure displaces the gas. The gas is not destroyed. It is simply moved aside. What remains are cavities where the gas once was. These cavities are not short-lived features. They persist for tens of millions of years, long enough to be observed clearly today. In effect, they are scars. Scars left behind by repeated outbursts of energy from the galaxy's core. Each cavity marks a past episode of intense activity. Together, they form a record of the black hole's influence over time. Crucially, these cavities show that the black hole does not simply consume matter. It expels energy back into its environment. That energy reshapes the galaxy on scales far larger than the black hole itself. The cavities also explain why M87 forms so few new stars. By pushing gas outward and keeping it hot, the black hole starves the galaxy of star-forming material. The result is a massive but aging system, rich in energy, but poor in renewal. All of this points back to a single source: the center of M87. The cavities are not random. They are aligned. They are structured. And they are unmistakably connected to the core. So, what kind of mechanism is powerful enough to excavate entire clouds of gas on this scale? The cavities inside the galaxy of Messier 87 point to a focused and sustained source of energy. That source reveals itself most clearly in the form of jets. Emerging from the immediate vicinity of the central black hole, these jets are not subtle features. They are among the most dramatic structures ever observed in a galaxy. In M87, a jet extends outward from the core in a narrow, well-collimated beam. It stretches thousands of light-years into intergalactic space. This jet is visible across multiple wavelengths. In radio light, it appears as a long, continuous structure. In optical and ultraviolet light, it breaks into bright segments. These segments are known as knots. They are not stationary. Over time, Astronomers have watched these knots move. They travel outward along the jet, away from the galaxy's core. By tracking their motion, scientists can measure how fast the jet material is traveling. The results were startling. Some knots appeared to be moving faster than the speed of light. At first glance, this seems impossible. According to the laws of physics, nothing with mass can exceed light speed. Yet the measurements were consistent. Independent observations confirmed the same apparent speeds. This phenomenon became known as superluminal motion. Crucially, the word apparent matters. The jet material is not actually breaking the cosmic speed limit. Instead, the illusion arises from geometry and timing. The jet of M87 is oriented at a small angle relative to our line of sight. This means the material is moving almost directly toward us as it travels outward. Light emitted from different positions along the jet does not reach Earth at the same time. Our brains reconstruct these signals into a single motion. The result is an apparent speed that exceeds light, even though the true speed does not. In reality, the jet material is traveling at speeds very close to light speed. This alone makes the jets extraordinarily powerful. Accelerating matter to such velocities requires immense energy, and that energy is delivered in a remarkably organized way. The jets remain narrow over enormous distances. They do not quickly disperse or lose coherence. This stability allows them to push deep into the surrounding gas. As they advance, they transfer energy to the environment. That energy inflates the cavities seen in X-ray images. In this way, the jets provide a direct physical mechanism for carving the galaxy. They connect the smallest scales near the black hole to the largest structures in the galaxy. The black hole itself is tiny compared to the galaxy. Yet through these jets, its influence reaches far beyond its immediate surroundings. This realization changes how we think about black holes. They are not merely sinks of matter. They are engines capable of reshaping entire galaxies. Still, one mystery remains. If these jets are not truly faster than light, what exactly creates the illusion that they are? The apparent superluminal motion seen in the jets of Messier 87 presents a quiet but profound tension. We measure speeds that seem to break one of the most fundamental limits in physics. And yet, nothing in the underlying theory appears to fail. The laws remain intact. The universe is not contradicting itself. Instead, the contradiction exists in how we observe motion across vast cosmic distances. To understand this illusion, we must step away from intuition shaped by everyday experience. On Earth, distances are small and speeds are slow compared to light. Light effectively arrives instantaneously. But in astrophysics, light itself becomes part of the measurement problem. The jets of M87 are not moving sideways across the sky. They are moving almost directly toward us. The angle between the jet and our line of sight is small, but crucial. When material in the jet emits light, that light begins a long journey to Earth. Moments later, the same material has moved closer and emits light again. The second burst of light has a shorter distance to travel. As a result, the two signals arrive closer together in time than they were emitted. When we reconstruct this sequence, the motion appears compressed. Distance divided by time gives a speed that looks impossibly high. Nothing is actually exceeding the speed of light. The illusion emerges because light itself is part of the timeline. This effect is purely geometric. It depends on angle, velocity, and distance. Change the viewing angle slightly, and the illusion disappears. Viewed from the side, the same jet would look entirely ordinary. This realization preserves the integrity of physics. Relativity is not violated. Causality remains intact. What we are witnessing is not a breakdown of natural law. It is a reminder that observation is never neutral. How we see depends on where we stand. Once the illusion is stripped away, something even more remarkable remains. The jets are still moving at velocities extremely close to the speed of light. This is not a trick of perception. It is a physical reality. Accelerating matter to such speeds requires a mechanism of extraordinary power. Not momentarily, but continuously, not chaotically, but in a tightly focused flow. The geometry explains why we were misled about speed, but it does not explain the source of the energy itself. And that is where the deeper mystery now lies. If nothing is truly moving faster than light, then what kind of engine can push entire streams of matter to the very edge of that limit? By the time we reach this point, one fact is unavoidable. The jets of Messier 87 are not gentle outflows. They carry staggering amounts of energy, enough to reshape gas clouds thousands of light years away, enough to regulate the evolution of an entire galaxy. That immediately raises a practical question. Where does all this energy actually come from? The answer does not begin inside the black hole. It begins just outside it. Surrounding the black hole of M87 is a structure known as an accretion disk. This disk is formed from gas and dust drawn inward by gravity. But rather than falling straight down, the material begins to orbit. Conservation of angular momentum forces it into a flattened disk. At first glance, this may seem like a passive structure. In reality, it is one of the most violent environments in the universe. Different layers of the disk orbit at different speeds. Inner regions move faster than outer ones. This difference creates friction and turbulence. That friction converts orbital motion into heat. Temperatures rise to extraordinary levels. In some regions, matter reaches billions of degrees. At such temperatures, atoms are torn apart. Electrons are stripped from nuclei. The disk becomes a glowing plasma. This plasma radiates intensely across the electromagnetic spectrum: X-rays, ultraviolet light, radio waves. The accretion disk is already releasing enormous energy before anything crosses the event horizon. Importantly, not all of the infalling matter ends up inside the black hole. A significant fraction never makes it that far. Instead, it becomes part of a complex, dynamic system. One of the key ingredients of that system is magnetism. The plasma in the disk carries electric charge. As it moves, it generates powerful magnetic fields. Those fields do not remain orderly. They are twisted and stretched by the rotation of the disk. Near the poles of the black hole, the geometry changes. Magnetic field lines become tightly wound. Energy builds up in these twisted structures. Eventually, the system finds a way to release it. Instead of falling inward, energy is redirected outward. Along the rotational axis of the system, this is where the jets are born. They are not simply streams of matter. They are channels through which energy escapes. The magnetic fields act like rails. They guide charged particles into narrow, focused beams. As the particles accelerate, they carry energy far from the black hole, much farther than gravity alone could ever reach. In this picture, the accretion disk is not a mere byproduct. It is a power plant. It converts gravitational energy into radiation and motion. It feeds the jets without requiring matter to disappear into the black hole. This explains something subtle but important. The black hole itself does not need to be violently active all the time. As long as matter flows through the disk, energy can be extracted. The jets can persist for millions of years, sustained by a steady process rather than explosive events. Yet even this powerful mechanism may not tell the whole story. The energy budget of M87's jets is enormous. In some models, it pushes the limits of what the accretion disk alone can supply, which leads to a lingering doubt. Is the disk doing all the work, or is the black hole itself contributing something more? If matter falling in is not the full answer, could the rotation of the black hole be part of the engine? Up to this point, we have followed the flow of energy from matter falling toward the black hole, gas spiraling inward, friction heating the accretion disk, magnetic fields channeling that energy into jets. It is an elegant and powerful picture. But as we push this explanation to its limits, questions begin to surface. In some cases, the energy carried by the jets seems almost too large, too persistent, too efficient, as if the accretion disk alone might not be the whole story. That suspicion leads us to a more radical possibility. What if the black hole itself is contributing energy, not through matter falling in, but through its own rotation? The black hole at the center of Messier 87 is not static. It is spinning. And it is spinning extremely fast. In astrophysics, rotation is not a minor detail. It fundamentally alters the structure of space-time itself. Around a rapidly rotating black hole, space is not simply curved. It is dragged along with the rotation. This effect is known as frame dragging. Nothing nearby can remain completely at rest. Everything is forced to move. This leads to the formation of a remarkable region just outside the event horizon, a region called the ergosphere. Inside the ergosphere, space-time is dragged so violently that all motion is compelled to follow the black hole's rotation. You cannot stand still there. Even light is forced to swirl. Crucially, the ergosphere lies outside the event horizon. This means interactions can occur without matter being lost forever. In theory, this opens a door to something extraordinary. Energy can be extracted from the black hole's rotation. The black hole slows down, ever so slightly, and that rotational energy is transferred outward. This idea was first explored decades ago. At the time, it seemed almost philosophical, a clever thought experiment rather than a practical engine. But modern astrophysics has given the idea new weight. When magnetic fields are added to the picture, the process becomes far more efficient. A rotating black hole threaded by strong magnetic fields can act like a generator. The rotation twists the magnetic field lines. That twist drives powerful electric currents. Energy flows outward along the rotational axis. In this framework, the jets are not powered only by infalling matter. They are partially powered by the black hole's own spin. M87 is considered one of the strongest candidates for this mechanism. Its jets are exceptionally powerful. They remain stable over immense distances, and they appear to tap into an energy reservoir that goes beyond simple accretion. This does not mean the theory is proven. Directly measuring black hole spin is extraordinarily difficult. Separating disk-powered energy from spin-powered energy is even harder. What we have are clues, not certainties, patterns that suggest rather than confirm. Still, the implications are profound. If black holes can lose rotational energy, they are not just endpoints. They are dynamic participants in cosmic evolution. They do not merely consume, they transform. In this view, the black hole of M87 is not only a devourer of matter, it is a cosmic engine, converting gravity, motion, and magnetism into structure and order. Yet even this picture leaves us with one final uncertainty. How much of the jet's power comes from matter? And how much from spin we do not yet know? And perhaps that uncertainty is the most honest ending of all, because it reminds us that even when we see a black hole, we are still only beginning to understand what it can truly do. M87 star was not just the first black hole humanity ever saw. It was the first moment we realized something deeper. That seeing is not the same as understanding. The image gave us a silhouette, but everything that truly matters lies in what that silhouette implies. A galaxy shaped by invisible forces, energy flowing where matter should have fallen. A black hole that does not only consume, but actively reshapes its surroundings. Perhaps this is what makes images like this so powerful, not because they give us answers, but because they ask better questions. Every new image we capture of the universe is not an ending. It is an invitation to look deeper, to question more carefully, and to accept how much remains unknown. If you would like to continue exploring the unseen structures that quietly shape the cosmos, you are welcome to join us. Thank you for watching.